Hello dear subscriber and welcome to this the lesson number 9, some typical system cubes. We will see in this lesson the most typical systems we encounter in our daily work, and we will analyze for these systems how to build, how to construct, how to draw the cube of the system. In the next lesson, the last one, we will combine all this with the cubes of the pumps in acting or working in series and in parallel. So let's start with this, the lesson number 9. We have here the most simple system of all. Two vessels connected by the pipe where the pumps is installed. We have the suction pipe upstream the pump and the discharge pipe downstream the pump. Downstream the pump we have first a check or a non-return valve, and after that a shut-off valve. We have the difference between the two surfaces of the liquid, delta Z1 and 2, and the atmospheric pressure is acting over the liquid surfaces. We already know that the flow rate is the same for every one of the pipes, since this system is in series, so the flow rate S is equals to the flow rate D at the discharge pipe, and the pressure or the head losses between the point 1 and the point 2, or the section 1 and the section 2, are equal to the sum of the pressure or head losses at suction pipe plus the head losses at discharge pipe. We would like to draw the curve, the H versus Q curve. Remember, we select, since these systems are in series, we select a fixed value of flow rate. The flow rate will be the same in every one of these systems, and we already know. We can draw the head losses curve for the suction pipe. We have the specific head losses for this value of Qx. We can draw also the head losses curve for the discharge pipe, and the corresponding value of the head losses for this value of flow rate Qx, and adding this to the pressure losses of the discharge pipe, we can obtain, as we already know, the curve or the head losses curve for whole the system, HL1, 2. If we add to these head losses the value of the static head, we obtain the curve of the system, the H versus Q curve of the system. By moving this over the static head, we obtain this curve. The intersection or the point where this curve intersects the flow rate at point X is the value corresponding to the head, total head, Hx. Let's analyze another case. What is different here from the previous case? That the discharge pipe is located, or the pipe discharge above the liquid level. This is not a submerged yet, but it discharges freely in atmosphere. So what is the head or the static head, the geodetic head that we should consider in this case? The section 2 that is located above the liquid surface. So this will be now the difference in geodetic head between the discharge section and the suction section and the initial section, let's say. Here we have the same. This is pipes are in series, so we have the same flow rate for every one of these pipes. I mean the suction pipe and the discharge pipe. And the head losses between the section 1 and section 2 are, of course, the sum of the pressure losses or the head losses of every one of these pipes, I mean discharge section. Let's draw the curve. As usual, the system is in series, so we should select a fixed value of flow rate, Qx, draw the curve for the head losses of the suction pipe and the corresponding head to this flow rate. This flow rate X, the same for the discharge pipe in orange and the HLG, and the corresponding head losses for this point. We add the value of HLS to the value of HLD, and we obtain of course the losses, the total losses of the system. Again, we should use this equation, the energy equation, but now we can see in the equation this term that corresponds to the kinetic energy at the exit of the pipe at section 2. See that this value can be incorporated into the, or is usually incorporated as a part of the head losses between section 1 and 2. This is an accessory, the discharge of a pipe. Since all velocity is or kinetic energy is lost after this discharge, the value of K, you can find everywhere that the value of K, but sudden discharge is equal to 1. All the kinetic energy is lost. So we can include this in the value of the pressure losses between these 2 points. So to find the system curve, we have to move this curve over the static head line to obtain the curve of the whole system with the corresponding value of the head Hx. We will do the same for all these cases we are analyzing today. The next case, what is the difference between this and the previous one? That the suction pipe trespass the liquid surface. We have an inlet pipe, a submerged inlet pipe. What is the reference section we should consider, we should take into account, we should select to apply the energy equation? The inlet of this pipe, of the suction pipe, or the liquid surface? Of course, the liquid surface is the section we should select. So the section 1 will be located over matching the liquid surface where the atmospheric pressure is acting on. This would be the difference in geodetic head, delta Z 1.2. The same will happen for flow rate and pressure losses, since this system is in series. And to draw the graphic, well, we will do the same. Select a fixed value of flow rate, draw the curve of the head losses for the suction pipe, the corresponding head losses for this value Q, the head losses for the discharge pipe, and adding this curve in series, I mean adding the pressure loss, the head losses and the pressure losses, we obtain the curve of the system. By moving this curve over the line corresponding to the static head, we will obtain the curve of the system, or of the system curve. And in the intersection of this curve with the vertical line corresponding to the flow rate Qx, we obtain the value of the head for this flow rate. The next case, what is the difference between this case and the previous one, or all the previous cases? That the pressure acting over the liquid surfaces is different than the atmospheric pressure. It could be higher, could be lower. This is, for example, a typical case of a boiler feed water system, where we are transporting water or moving water, feed water, from the deaerator that would correspond to the vessel 1 at pressure P1. Normally this pressure is a low pressure, or even in some cases vacuum, and to the pressure of the boiler drum P2, that is normally much higher. So the same will happen for flow rate and head losses in this system is in series. So we will do the same here, draw the curve or head losses curve for the suction pipe, the same for the discharge pipe. We can draw the overall head losses between section 1 and section 2. And now what is different? Or what is different here? That we have to include within the static part of the head corresponding to the difference in hydrostatic pressure, P2 minus P1. We know that this component plus the georetic head conform the so-called static head. This part of the head doesn't change with the flow rate, as we already know. So we can draw here a line that doesn't change with the flow rate, and we can add the head losses over this line to obtain the curve H, or total head of the system versus Q for this system. And finally, we obtain the value of Hx, of course. The last case is the case number 5. We have here the most simple case. Two vessels over this vessel, the atmospheric pressure is acting, and we have two pumps with the suction line and the discharge line in parallel with another pump, so one pump to another, and this line that are in parallel between them are in series with the common system pipe. I mean, for pump 1 we have the pipe A and pipe B in series. For pump 2 we have the pipe C and pipe D in series. But the combined curve of the system AB is in parallel with the combined curve of the system CD. These two systems are in parallel. So we will obtain a combined curve of these two systems, and we will add this curve to the one that is in series to this common system, that is the pipe E. So delta Z, of course, is the difference between the surfaces and the liquid surfaces in a static head. In theoretic head, sorry. We can draw the graphite here. This first graphite or this curve is the combination of the pipe A and B in series. Normally, the next system, I mean the system, the combined curve C plus D in series, is match this curve because normally these systems are symmetrically, are identical. But to show here how to sum every system, we will consider that in this case the head, the pressure losses curve is different from one between those systems. So again, we have represented here in green the head losses curve for the system, combined system AB in series. We will represent also the same for the different system CD in series, both C and D, and we will add the system AB plus system CD in series. Please note that although the curve of the systems, those systems that are in parallel is or could be different one from another, but we should consider that the pressure losses are between the common 2 points. In this case will be the liquid surface, the initial point, and the end point of this point in parallel is this point where the pipe A begins. So the pressure losses are the same per every one of these systems. What happens is that the flow rate accommodate in every one of these systems that could have different characteristic curves to obtain the same pressure losses. So to draw the curve in parallel, we select a fixed value of the pressure losses, and we will sum the flow rates running from every one of these systems in parallel to obtain the combined curve in parallel. What else? We have still to add to this curve, to this combined curve, the system that is in series with them. We have drawn here the curve, the head losses curve of system E. So in this case, since these systems are in series, we select a fixed value of flow rate. We have the head losses, the pressure losses of this system E, and we should add this to the head losses of the combined system AB plus CD. And doing this for several points, we obtain the total curve or the head losses curve of all the system between the section 1 and the section 2. And again, we have to add to this curve the static head to obtain the curve H versus Q of the system. That is the sum of the static head but the head losses. Well, this is all for today. In the next lesson, as I mentioned before, we will see in the last lesson how to combine all this with pumps in series, or running in series, working in series, and in parallel. So I will be waiting for you in the next lesson. Bye bye. Adios, amigos.